So what we're going to start talking about now is chemical reactions. So we're going to talk about these chemical reactions and how we describe those chemical reactions on paper, which involves using these chemical equations. We need to worry first about something called stoichiometry. So this is the branch of chemistry that's concerned with this combining ratios of atoms and molecules in their reactions. Okay, this is going to be very, very important to chemistry. We're going to use it all the time. A large portion of chemistry involves these chemical reactions, and we need to understand what these equations are showing us. So when we look at a chemical equation, we have one here. We have CH4 plus 2 O2s goes to form 1 CO2 plus 2 H2Os. Okay, now one thing from this equation you need to recognize, reactants are going to be on the left, products are going to be on the right. Now the other thing we want to recognize is something called stoichiometric coefficients. Those are the numbers out in front of those. So in front of CH4 there's a 1. We don't write 1, it's just implied if there's nothing written there. Okay, in front of the O2 there's a 2, 1 in front of the CO2, and a 2 in front of the H2O. Those are what we call the stoichiometric coefficients. So what are they actually telling us? Well, if we look at a picture of this, it's telling us in a chemical reaction we'd have 1 molecule of CH4 reacting with 2 molecules of O2 to form 1 molecule of CO2 and 2 molecules of H2O. So it's actually telling us how things are combining in this chemical reaction that we can visually see. Right, so these chemical equations are very, very important in representing chemical reactions. Now these chemical reactions and equations are going to revolve around this idea called law of conservation of mass. Law of conservation of mass states that matter cannot be lost in any chemical reactions. Okay, matter can't be created nor destroyed. It's probably a form of it that you've heard before. All right, what does this mean? Well, if I look at these two solutions on the left-hand side of the scale here, I've got a lead nitrate solution and a sodium chromate solution. The right-hand side, I've got certain masses. Okay, this is before I mix the lead nitrate and the sodium chromate. When I mix those two solutions, what happens is I form a precipitate, that kind of yellowish solid in there. But if you notice, the scale hasn't moved. So what I start with before the reaction is what I start with after the reaction in terms of overall mass. So I'm having lead nitrate adding to sodium chromate to form lead chromate and sodium nitrate. So if I look at this, I have 1 lead on the reactant side, 1 lead on the product side, 2 nitrogens on the reactant side, 2 nitrogens on the product side, 10 oxygens total on the reactant side, 10 oxygens total on the product side, 2 sodiums on the reactant side, 2 sodiums on the product side, and 1 chromium on the reactant side and 1 chromium on the product side. So if I look at the masses of these things, the masses of these compounds are different, but when I add them up, I get equal mass on either side. And that's what the law of conservation of mass is getting at. It's what I'm starting with in terms of the matter. It's what I'm ending with. All I'm doing in this process is rearranging how that matter is connected. Right? I'm breaking bonds and reforming bonds. Okay, another example we can look at here. Sodium is going to be in solid form. If I look at chlorine, it's a gas. It's a diatomic gas, so I have molecules of chlorine moving around fast. When I combine them together, I get well-ordered sodium and chlorine in that solid structure. But if I look at their masses, if I start with 7.7 grams of sodium, react it with 11.9 grams of chlorine, I'm going to end up with 19.6 grams of sodium chloride. What I start with in terms of mass is what I end up with in terms of mass. That's the law of conservation of mass. That's going to be very, very important when it comes to balancing equations. Now before we get into actually balancing equations, we want to look at these equations a little bit more. So the other thing to notice besides the formulas, besides the stoichiometric coefficients, you also need to recognize the different states that will be labeled. And these are the 4 common ones we're going to run across. S stands for a solid, L stands for a liquid, AQ stands for an aqueous solution, that means it's dissolved in water, G stands for a gas. One of the most common things that people confuse, they confuse a liquid and an aqueous solution. If I have something dissolved in water, it's aqueous. If I have a pure compound and it's melted, it's in liquid form, that's liquid. So if I take sodium chloride and put it in water, I make salt water. But technically it still looks like a liquid. Okay, but it's got something dissolved in it, which means it's not a liquid, it's an aqueous solution. So don't confuse liquid and aqueous solution. Liquid means it's something that's melted and it's in its liquid state. Aqueous means you have a mixture where something's dissolved in water. All right, so to better understand how to balance these equations, we need to understand the chemical formulas and the equations themselves. So when I look at these formulas, what do these formulas in this equation represent? Well, they're going to help tell us how many atoms of the different elements we have. So when I look at these formulas by themselves, if I look at C7H8, how many carbon atoms are represented there? Well, that's 7. How many oxygen atoms are represented by that? Well, there's 0 in that formula, so we have none there. How many hydrogen atoms? It's 8. All right, let's look at our other reactant, O2. Has 0 carbon atoms in that formula. Has 2 oxygen atoms in the formula. And it has 0 hydrogen atoms in the formula. CO2 has 1 carbon atom, has 2 oxygen atoms, has 0 hydrogen atoms. H2O has 0 carbon atoms, 1 oxygen atom, 2 hydrogen atoms. Okay, so it's important that you first recognize what are these chemical formulas telling us. But if you notice, the number of atoms of each type for our products isn't equal to the number of atoms of each type for our reactants. All right, so now let's look at stoichiometric coefficients. First off, C7H8, is that a reactant or a product? Well, it's a reactant. How many molecules do we have in this reaction? Well, there's no number out in front of it, which means we have 1 molecule. What about O2? That's a reactant, and we're going to have 9 molecules in this reaction. What about CO2? That's a product. We're going to have 7 molecules in the reaction. What about H2O? That's a product. We're going to have 4 molecules in the reaction. All right, so how are those stoichiometric coefficients, in other words, the number of molecules in the reaction, going to interact with those formulas for our totals? Well, when I look at this equation, the number of molecules in the reaction, I've already said, that's those coefficients out in front of those formulas. If I have 1 molecule of C7H8, how many total carbon atoms do I have? Well, I have 7. How many total oxygen? 0. How many total hydrogens from that? I have 8 of them. If I have 9 molecules of O2, how many total carbon atoms do I have? None from that formula. How many total oxygen atoms do I have? Well, I no longer have 2 because I have 9 molecules of it. So 9 times 2 gives me 18. How many hydrogen? 0. What about the 7 molecules of CO2? I'd have 7 atoms of carbon. I'd have 14 atoms of oxygen. And I'd have 0 atoms of hydrogen from that formula. What about the 4 H2Os? 0 carbons, 4 oxygens, 8 hydrogens. So all we're doing is taking those stoichiometric coefficients times the number of atoms in the formulas. But when we look at the totals overall, if we look on the reactant side, total number of carbon atoms we had on the reactant side is 7. Total number of oxygen atoms was 18. Total number of hydrogen atoms was 8. If we look on the product side, total number of carbon atoms was 7. Total number of oxygen atoms was 18. Total number of hydrogen atoms was 8. So we've maintained that law of conservation of mass. However many carbon, oxygen, hydrogen atoms we started with, we ended up with the same number of each type on the product side. All we've done is rearrange how those things are connected. That's it. And that's what we want to focus on, and it's going to be important when we start considering balancing chemical equations. So we're just going to go through another example of this. We're going to go fairly quickly through it. So if I look at mercury fulminate, it's an explosive used in detonators. Everybody likes explosions, so I threw this in as a fun little fact. But what we're going to do is take that mercury fulminate, and it starts in solid form. When it goes through its reaction, it actually breaks down into mercury in its gas form, carbon monoxide in its gas form, and nitrogen in its gas form. Okay, so when we look at this balanced equation, we can get some basic information out of it. First from the formulas. So for that first formula there, for the mercury fulminate, it's got 1 mercury atom, 2 carbon atoms, 2 oxygen atoms, 2 nitrogen atoms. For mercury itself, there's one mercury atom. Got no carbon, no oxygen, no nitrogen from that formula. CO, no mercury, one carbon, one oxygen, no nitrogens. And N2, no mercury, no carbons, no oxygens, two nitrogens. All right, so are we dealing with reactants or products and the number of molecules in the reaction? So the mercury fulminate, well, that's a reactant. We have one molecule in this reaction. What about the mercury? Well, that's a product. We have one of those. What about CO? It's a product. We have two of those. Don't forget that coefficient of 2 out in front. And then N2, that's a product. We have one of those. All right, so what does this do in terms of our total number of atoms? Well, for our total then, we have, for the first formula times the molecules, would be one mercury, two carbons, two oxygens, two nitrogens. For the mercury times the 1, we just got one mercury atom. We have 0 carbons, 0 oxygens, 0 nitrogens from that. For the two molecules of CO, we have 0 mercury atoms, 2 carbon atoms, 2 oxygen atoms, and 0 nitrogen atoms. And for one molecule of N2, we've got 0 mercury, 0 carbon, 0 oxygen, 2 nitrogens. So once again, when we look at our totals, the total number of each type of atom on the reactant side equals the total number of each type of atom on the product side. So our law of conservation of mass has been maintained. So what we're going to look at next is how we get those stoichiometric coefficients. But what you need to keep in mind is, remember this law of conservation of mass. So the number of each type of atom on the reactant side has to equal the number of each type of atom on the product side. Those have to be equal in order for us to have a balanced chemical equation. All right, now when we're looking at balancing chemical equations, I'm going to give you a couple of hints. All right, you can pay attention to these or not. It's up to you, but I find them very, very useful, and I think they'll make your life a lot easier when it comes to balancing these equations. All right, so the first one. Start from the left of the equation, balance elements as you go to the right. Okay, it just gives you an order to start with, and it helps you stay focused on balancing the equations. Now, another hint to kind of go along with that one, though, is balance everything but hydrogens and oxygens first, if possible. So as you start your way from the left and work your way to the right, if you run into hydrogens or oxygens, skip them. Because what happens a lot of time in these equations is, once you're done balancing everything else, a lot of times the hydrogens and oxygens are already balanced, so you don't need to worry about them. Or it becomes easier to balance the hydrogens and oxygen. Okay, so do those last, if possible. If you have a polyatomic on both sides of the chemical equation, don't separate it up into its elements. Treat it as one thing. Okay, so if you have polyatomic in the reactant side and polyatomic in the product side, don't break it up. It's going to make it easier to balance. Keep track of the total atoms on each side of the equation. Remember, we're trying to get equal number of atoms of each type on both sides of the equation, so keeping track of it is going to be important. So this one's a little bit longer. If you have an element that's in one compound on one side of the equation, and those side could be either product or reactant side, but it's in 2 or more compounds on the other side of the equation, you may want to switch to using fractions first to balance the equation. Once you're done balancing with that fraction, though, you need to remove the fraction by multiplying all the coefficients by the denominator of that fraction. Okay? So I know you completely understood what I said there, right? Don't worry. We're going to go through an example here later on, and I'm going to explain it a little bit more. Okay, but this is just something so that you have something to look back at and see to remind you of these hints. Okay, so we're going to go through number 5 in an example later on. All right, and the last thing. When you're done balancing an equation, double check to make sure you have the smallest whole number ratio. You always want the smallest whole number ratio. So if you have a chemical equation that has coefficients of 2, 4, 4, and 2, well, those can all be divided by 2. So it should actually be coefficients of 1, 2, 2, and 1. Okay, so always double check at the end that you got the smallest whole number ratio.